Good afternoon, everyone. In the previous lecture, we discussed about the two laws of the Newton's, right? The first law and the second law of Newton. Today, we'll be starting with the concept of impulse. It's a very important concept. So, we have heard about the impulsive forces, right? So, we'll be discussing what actually the impulse is, what impulse actually means, right? So, impulse is nothing whenever a large force acts on a body for a very short interval, right? When a large amount of force acts on a body is applied on a body for a very short interval of time, then the force we call as impulsive force, right? And what does this force do? It actually changes the momentum of a body suddenly, right? Or we can say it's a force which changes the momentum of a body, right? So let's suppose this is a body on this surface, right, of mass m, and we are applying an impulsive force, right? The force acts on a body, this is the impulsive force, for a very short interval. For very short intervals such that delta t tends to 0, or we can say that this is a very short interval. It can be like 0.1 second of time or 0.01 second of time, right? So it's a very small amount of time for which the force acts on a body, right? Because of that, the huge change in momentum occurs in the momentum of a body, right? So impulsive forces are very large amount of forces which acts on a body for a very short interval. We know according to Newton's second law of motion that F is equal to dp over dt. That's the rate of change of momentum with respect to time, right? Force is directly proportional to the rate of change of momentum with respect to time, or F is equal to dp over dt, right? So if we take this force, if we integrate this force with respect to time, right? We'll be integrating this change in momentum also, right? There will be a small change in momentum dp. Let's integrate it. And let's suppose for 0 to t time, and from momentum p initial to p final, right? This is nothing. This will be equal to p with the limits p initial to p final, right? So this is nothing. It's p final minus p initial. That's the change in momentum, right? Delta p, delta p. So what impulsive force does actually, it actually changes the momentum of a body. So this is what we call as impulse, right? This is the impulse. This is the impulse, right? So if force is a function of time, right? And if we integrate force with respect to time with the proper limit, we will get the change in momentum. Or that will be the impulse on a body, right? Impulse on a body. Impulse on a body. And let's suppose if f is a constant, right? If f is a constant, we'll take it out of this integral. So f will be taken outside this integral. We'll integrate it from 0 to t with respect to time. That will be equal to change in momentum, right? And this f is nothing. It's a constant force, or we call it as average force, right? F average. So it will be multiplied by this time delta t. That will be equal to change in momentum, right? So from this, we can also calculate the average force. Average force will be nothing. That will be equal to delta P over delta T, right? So this is the average force, right? So average force is nothing. It's del P over del T. That's delta P is the change in momentum, and delta T is the interval of the time, right? Time interval, right? So this is how we define the impulse on a body, right? So impulse is nothing. It's the change in momentum, and average force we can actually calculate change in momentum upon the time interval, right? And this is the integral of force with respect to time, right? From 0 to t. That's equal to delta p. That's the change in momentum, right? So if we plot a force with respect to time, right? If there is a plot between the force and time, let's suppose this is the plot between force and time. The plot between force and time. Let's suppose this is the plot between force and time. And then the area under this curve will be given by this integral, right? So this integral does represents actually area under force time graph. Area under force time graph, right? Force time graph. So it's nothing, it's actually change in momentum, right? Change in momentum. So area under force time graph gives us change in momentum. Change in momentum. So if we have to calculate the change in momentum when the force versus time graph is given, we will just calculate the area under that graph. That will give us the change in momentum, right? So what are the applications where do we use actually this concept of average force of the impulse? You know that whenever a cricketer lowers his hands while catching ball, right? What cricketer actually does is that it actually the change in momentum is actually a constant there, but what it does actually it tries to increase the time interval of momentum change, right? It increases the time interval of momentum change. When the time interval of momentum change is increased, right? We know average force is nothing. Average force is equal to delta P over delta T, right? So when a cricketer, while catching a ball, lowers his hand, it increases the time interval for the same change in momentum. When the time interval is increased, the average force acting on the hands of a cricketer actually decreases, right? It actually decreases. So he can save himself from getting hurt, right? So that's how the cricketer uses this concept of change in momentum or the impulse or the average force. It increases the time interval for the change in momentum, and consequently, the average reaction force on his hands actually decreases, so that his hand does not get hurt, right? Also, we use the same concept in the shockers which are provided in vehicles also, right? To avoid any jerks, right? Shockers also does the same type of thing, right? Which are used in the vehicle to avoid any jerks, right? Let's suppose a person jumping on a hard cement floor receives. It's always that person jumping on a hard cement floor receives more injury than a person jumping on muddy or sandy road, right? Because on hard surface, what happens is that the change in momentum is actually same for the both the things, but on hard cement surface, the time interval will be actually very short, right? When the time interval will be very short, for which actually the same momentum change, it means that the average force acting on that time when the body falls on the hard floor or the cement floor, the average force actually increases. Because of that, what happens is that the person gets injured easily, right? Rather than falling on a muddy or sandy road, right? Because in muddy and sandy road, the time interval between the change in for the change in momentum actually increases, so as to decrease the average force acting on a body, right? So that's how actually uh, it's always easy to jump on muddy or sandy road rather than on a hard surface, right? Let's try to solve some of the questions related to this impulsive force. A question is a football of mass 0.8 kg coming towards player with a velocity of 5 meter per second, right? Player hits straight back the football with velocity of 10 meter per second. If the contact time is 0.02 seconds, then the average force involved is, right? So it's the question like this. Football of mass 0.8 kg is actually coming towards a player, right? This is the football of mass 0.8 kg, right? The mass of this ball is 0.8 kg. It's coming towards a player with a speed of 5 meter per second, right? With a speed of 5 meters per second. Now, what happens is that this ball is hit straight back with a velocity of 10 meter per second. Now, this ball is hit straight back with a velocity of 10 meter per second, right? 10 meter per second. And the time of contact between the ball and the player is actually delta t, that's given as 0.02 seconds, right? 0.02 seconds. We have to calculate the average force. We know the average force is nothing, is the change in momentum. That's delta P over delta T. So this is nothing, this is the average force acting on a body, right? So change in momentum will be given as final momentum minus initial momentum, right? Final momentum minus initial momentum Pi, right? So initially the body was moving along positive x-axis. We'll take this momentum as positive, right? It will be 0.8 multiplied by 5 I cap, right? And finally, this was the initial momentum, right? This was the initial momentum, and the final momentum is along negative x direction. We'll take it as negative. That will be minus 0.8 multiplied by 10, right? I cap, and minus initial momentum, that's 0.8 multiplied by 5 I cap, right? This is the change in momentum, right? So change in momentum is actually it will be 8 and minus 8 I cap, right? Minus 4, right? I cap. That will be equal to minus 12 I cap. Or if we talk about the magnitude only, right? If we talk about the magnitude only, there's a magnitude of this change in momentum. That's actually 12 kg meter per second, right? So this is the change in momentum, right? So the average force acting on this body is nothing. It's change in momentum, that's 12 upon the time for which this momentum change occurs is 0.02 seconds. That's 0.02 seconds, right? Or we can write it as 12 upon 12 upon 2, 12 upon 2 multiplied by 100, right? So the force acting on this body is actually 600 newtons. So average force acting on the body or the football is actually 600 newtons, right? So 600 newton is the average force acting on a ball, right? The question here is a body of mass 3 kg has an initial speed. A body of mass 3 kg has an initial speed of 4 meter per second, right? A force acts on it for some time in the direction of motion, right? A force acts on it for some time in the direction of motion. The force time graph is shown in figure. The final speed of the body is, right? You can see here we have there's a given force versus time graph, right? The fashion in which the force and time graph varies is given in this diagram, right? Initially, the speed of this body was given as 4 meter per second. The u initial speed u is given as 4 meter per second, right? And the mass of this body is actually 3 kg, right? That's equal to 3 kgs. Now we have to calculate the final speed for this body, right? And we know that the force under the force time graph, actually the area under force time graph gives us the change in momentum, right? This gives us the change in momentum, right? For the entire time, if we calculate this area under this curve, we will get the change in momentum, right? We can write here area under force time graph, that's the FT graph, actually gives us the change in momentum. Gives the delta P, that's the change in momentum, right? It gives us the change in momentum, right? So if we calculate the area under this force time graph, we'll get the change in momentum, right? So we'll try to calculate the change area of this graph one by one. So this is the first figure. There's the triangle here. This is the rectangle here, right? This is trapezium here, and this is once again the rectangle here. We'll try to calculate the area of all these shapes here one by one, right? That's so the total area will be equal to area of this triangle. Triangle will be half base into height, right? Base is 2 and height is equal to 4, right? We'll multiply by 4 plus area of this rectangle, that will be the base multiplied by height. The base is 2, right? And the height is once again 4. We'll multiply by 4. And area of this trapezium is nothing, it's the half of sum of parallel sides. So parallel side is actually 4 plus 3, right? It will be 4 plus 3 into the distance between them. And the distance between here, this parallel sides of this trapezium is actually 0.5, or we will multiply it by half, right? And finally, we're once again left with this rectangle here. The area of this rectangle will be, it has to be equal to base is 2, and the height is 3. We'll multiply it by 3, right? So this and this will get cancelled. We'll be left here with 4, right? That's 8 plus That will be 7 upon 4, right? 7 upon 4 plus 6, right? So it will be 14. 14 plus 4 will be 18, right? 18 plus 7 upon 4, right? Or we can write it equal to as 18 plus 7 upon 4 will be, it will be 1.7, right? It will be 1.7, 1.7, or we can write it equal to as 19.7. So this is actually the change in momentum, right? This is actually the change in momentum, right? This is actually the change in momentum, right? So 19.7 is the change in momentum. And this change in momentum is nothing, it's the final momentum minus the initial momentum, right? That's P final minus P initial. That comes out to be 19.7, right? 19.7. Or we can say that final momentum will be equal to 19.7, 19.7 plus this initial momentum, right? Initially, the body was moving with a speed of 4 meter per second, and with the mass of the body is given as 3 kg, right? We'll just add it 3 multiplied by 4, right? So it will be 12, right? It will be equal to 12. So it will be equal to 31.7, right? 31.7. So final moment, we have to calculate the final velocity. Final momentum will be the mass multiplied by the final velocity. That will be 31.7, right? Or we can find the final velocity as 31.7 over 3, right? Over 3 meter per second. So this will be the final velocity of this body, right? So we calculate the final speed or the final velocity of this body using the force time graph, where we actually calculated the change in momentum, right? From there we calculated the final velocity acquired by the body, right? So let's again discuss similar question here, right? It's the similar question. The question is that figure shows an estimated force time graph for a baseball struck, right, by a bat. Uh, it shows an estimated force time graph for a baseball struck by a bat, right? From this curve, determine the impulse delivered to the ball and average force exerted to the ball, right? So, impulse delivered to this ball will be nothing. It will be actually the change in momentum, right? It's a force time graph, right? It's a force time graph. So, impulse delivered to this board will be given by actually by the change in momentum, right? So impulse delivered will be change in momentum of this body, right? That's delta P. That's equal to delta P, right? So we know that change in momentum of force and time graph is actually given by the area under the curve for this force and time graph, right? We have been given this graph, which will just calculate the area under this curve, right? It's a triangular shaped here. We'll try to calculate the final, we'll try to calculate the area of this triangle here. If we calculate the area of this triangle, we'll get the change in momentum of the impulse, right? So area of this triangle, right? Area of this triangle, area of force time graph will be delta equal to delta P. That's actually the impulse, right? That's actually the impulse. So let's try to calculate this area. You can see that area of this triangle is actually half base multiplied by height. The base of this triangle is actually 2.5 minus 1. That will be 1.5, right? It has to be 1.5. And height of this triangle is actually 18,000, right? That's given us 18,000. Let's multiply it by 18,000, right? So it will be 3 by 4 multiplied by this 18,000, right? 18,000, right? So it will be equal to 3 multiplied by 4,500, right? That will be equal to, it will be 13,500, right? 13,500, right? So it will be change in momentum is actually equal to 13,500, right? 13,500 will be the change in momentum, right? Or this will be the same impulse acting on this body, right? So 13,500 is the impulsive force or the impulse acting on this body, and calculating the average force. So average force on this body will be change in momentum upon the time interval for which the force acts on a body, right? The change in momentum is 13,500, right? Upon that time, I can see the time interval for which the force actually acts on a body is actually 1.5 seconds, right? It's 1.5 seconds. So we'll multiply divide it by 1.5. So it will be 13,500 upon 3 over 2, right? 3 over 2, right? So it will be 4, 5, right? It will be equal to 9,000. So 9,000 Newton will be the average force acting on this ball, right? So this ball was actually struck by a bat with a force of 9,000 Newtons, right? It's a very huge force. So we have another question here. A 200-gram tennis ball coming at a speed of 10 meter per second is hit straight back by a bat to speed of 20 meter per second. The magnitude of the average force F on the ball when it is in contact for 4 milliseconds with the bat. It's the similar question that we solved before also, right? We'll just quickly try to solve it. A 200-gram tennis ball is coming at a speed of 10 meter per second, right? The mass of this ball is given as 200 grams, right? That's equal to 0.2 kgs, right? 0.2 kgs is straight hit by a bat at a speed of 20 meter per second, right? It means that it will just reverse its direction, right? With a speed of 20 meter per second and mass is same, that's 0.2 kgs. And we have to calculate the time for which this momentum change occurs. The time for which this momentum change occurs is actually equal to 4 milliseconds, right? 4 milliseconds, that's 4 multiplied by 10 to the power minus 3 seconds, right? And we have to calculate the average force. So the average force will be once again equal to whatever be the change in momentum upon the time interval, right? Delta t. So change in momentum, we know it's final momentum upon final momentum minus initial momentum, right? Initially, the body was moving along x direction. We'll take that momentum as positive, and now finally it's moving along negative x direction. We'll take that momentum as negative, right? So final momentum is minus 20 meter per second, right? Minus 20 multiplied by 0.2 kg, right? 0.2 I cap, right? Minus 0.2 multiplied by 10 I cap, right? So it will be minus 4 minus 2 I cap, right? That's equal to minus 6 I cap, right? So minus 6 I cap is the change in momentum for this body, right? The average force will be F average has to be equal to minus 6. Let's forget about the sign of this force, right? Direction of this force. We'll just calculate the magnitude. That's 6 upon 4 into 10 to the power minus 3, right? So it will be actually 1.5 multiplied by 10 to the power 3, right? So it has to be equal to 1500 newtons, right? So 1500 newton is the average force which actually acts on this body, on this ball, right? Which changes its velocity from 10 meter per second along positive x direction to 20 meter per second along negative x direction, right? So 1500 newton will be the final answer. A hammer of mass 1 kg moving with a speed of 6 meter per second strikes a wall and comes to rest in 0.1 second. Calculate the impulse force, average starting force, average retardation of the hammer means average retarding acceleration of the hammer, right? So the impulse will be the change in momentum here also, right? That is P final minus P initial, right? And it comes to rest, so the final momentum has to be equal to 0, right? So the initial momentum is minus 1, that's the mass of this hammer, right? Multiplied with the speed, that's 6 meter per second. Or we can say the magnitude of this impulse is 6 kg meter per second, right? So this is the magnitude of impulse, right? So retarding force, average force will be delta P over delta T, right? That's actually equal to 6 upon 0.1 second. That's equal to 60 newtons, right? 60 newtons. And the average acceleration will be nothing. It will be force upon the mass of this body, right? Force is given as force is 60 newtons, and the mass of this hammer is 1 kg, right? So it will be 60 meter per second square. So this will be the retardation, right? 60 meters per second square will be the retardation. Now let's move on to the next topic. The next topic is our conservation of linear momentum, right? And the Newton's third law, right? Let's suppose we have this body, right? Initially of mass m, right? And initial velocity u, right? Initial velocity u. And we know according to Newton's second law of motion that unless and until we do not apply any force, right, or Newton's first law of motion, right, unless and until we do not apply any external force on this body, the state of motion of this body is not going to change, right? So initially the body was moving with velocity u in this direction, right? So if the velocity of this body is not going to change because there is no force acting on it, it means that the body will have the same momentum every time, right? So momentum of body can be changed only, or the state of motion of a body can be changed only when there is some external force acting on that body, right? So on this body, there is no external force acting on it, so it will continue to be in the same state of motion. It means it will have the same velocity vector, right? Same velocity vector, right? After any time t, if at time t equal to 0, the state of motion was this, then after time t equal to t seconds, right? The state of motion of this body is not going to change because there is actually no force acting on this body, right? Along the direction of a motion of a body, right? So we can say that the momentum here of the momentum of this body is actually the same at time t equal to 0 or time t equal to t seconds, or we can say the momentum of a body is conserved here only because there was no change in state of a motion, right? And the change of state in motion did not occur because of the absence of the external force, right? We'll just write the Newton's second law of motion here, right? That's F is equal to that's the dp over dt, right? dp over dt. So it's nothing, force is equal to rate of change of momentum with respect to time. So it means that if there is no external force on the body, right, it means F external. So the F external, if F external is equal to 0, it means there is no external force acting on this body, right? So F is equal to 0 here. And dp over dt, that's the first derivative of momentum with respect to time, is equal to 0. Or we can say P has to be a constant, right? We know derivative of a constant is always 0, so P has to be a constant, right? So P is constant, right? P is constant. P constant means P initial has to be equal to P final, right? And that's nothing, that's the conservation of momentum, right? Conservation of linear momentum. Conservation of linear momentum. Conservation of linear momentum actually says that when there is no external force acting on our body, then the momentum of a body remains constant or conserved. Whatever be the initial momentum of a body, same will be the final momentum of the body, right? If the external force is equal to 0, right? So let's discuss a bit about the Newton's third law of motion as well, right? Then we'll be discussing some of the questions related to conservation of momentum as well as Newton's third law of motion, right? So Newton's third law says that there is always an equal and opposite. Whenever there is an action force to every action, right? There is always a reaction force which is always opposite in direction, right? And the both action reaction pairs actually acts on two different bodies, right? So let's suppose that we have two bodies here, right? We have two bodies here, right? Body A and body B, right? Body A and body B. Now, if the body A applies some force on body B, right, in this direction, right, in this direction, let me call that this force as force on body B by body A, right? Then there will be equal amount of force by body B on body A, but in opposite direction, right? But in opposite direction, right? That means that action reaction force always occurs instantly as well as in pairs, right? It's not a delayed force, it's an instant action reaction force, right? So it means that the action reaction force always acts on two different bodies, right? On two different bodies and their opposite direction, right? So that's the Newton's third law, that to every action force there will be a reaction force, right? And it will be opposite in direction, right? And it will act on two different bodies and it will be simultaneous, right? It will be simultaneous. Simultaneous by we mean that it will be an instant action reaction pair, right? There will be no delay in the reaction force, right? When the action occurs, right? So that's the Newton's third law of motion, right? So there are some important points regarding this third law, right? So the first point is that about the isolated force, right, in nature. So whenever there is a action force, there always will exist a reaction force, right? So we can say that the action reaction force, it's not possible to have only action force and there will be no reaction force. They will always occur in pairs, right? So we cannot have isolated force in nature, right? They will occur in pairs, right? And the second point is that it's a simultaneous action force, right? Action reaction force is a simultaneous force. There is no time gap or the time delay between the action reaction force. So it means that we cannot actually say that there is actually any cause or effect of these after these action and reaction force, right? So it's not like that we can say reaction is the cause of the action force, right? Or its effect. So they are actually the simultaneous forces, right? There is no gap between time gap between the action reaction forces, right? So the third point is that it's actually applicable for both, whether the body is in motion, whether the body is in rest. So action reaction force will be there, right? If some force acts on a body at rest, then there will be reaction force also. If the force acts on a body in motion, then definitely there will be a reaction force also, right? So it's applicable for both, whether the body is at rest or the body is in motion, right? There is always action reaction forces, right? And the fourth point is that it's not always to have action reaction force without the with the contact of a body, right? So without the contact of a body, two bodies, we can have action reaction force, or like we have in gravitational forces, right? Whenever a body is applied by acted by the gravitational force due to earth, then the same amount of gravitational force is actually exerted by the body on the earth itself, right? So it's not necessary to have physical contact for the action reaction forces. Without any physical contact, there can be a action reaction forces also. You have a simple example of electrostatic force also. You have an example of gravitational force also. Gravitational force is also action reaction force, right? So that's a action reaction force without having any physical contact between the two bodies, right? So without any physical contact, we can have the action reaction forces, right? So one more important point is, that's the very important point. That's the whenever there is an action reaction force on two different bodies, right? So they will not never cancel each other, right? Action reaction force can never cancel each other, because the two forces cancel each other only when the two forces are actually acting on the same point or on the same body, you can say, right? Then only the two forces will cancel out, right? Otherwise, if the two forces are acting on two different points, right? Two different points or two different bodies, right? Then the two forces will not cancel out each other, right? Or we can say that the action reaction force cannot cancel each other, because the action and reaction force are actually act on two different bodies, right? So it's not possible to have the cancellation of action and reaction forces, right? So these were some of the important points regarding the Newton's third law of motion, right? And conservation of linear momentum. And with respect to these two concepts, that the Newton's third law and conservation of linear momentum, we'll be discussing some questions in the next lecture, right? So because the time is already up, so we'll be discussing some good questions in the next lecture. But till then, take care and goodbye.